Hello, my name is Thomas Freiling, and today I'll be presenting a paper called Face Flashing, a secure liveness detection protocol based on light reflections. So, a link to the paper is provided here, and authors of this paper are Di Tang from Chinese University of Hong Kong, Zi Zhao from Fudan University, Yingkan Zhang, Ohio State University, and Kehuan Zhang, Chinese University of Hong Kong. So introduction, background. Face authentication systems, FAS, are becoming more and more prevalent. Face information, however, is easily obtained and simulated, making face auth systems susceptible to attacks, i.e. faces pulled from social media, etc. So for liveness detection, LD, is the detection of whether or not the user is a real human. It's an important line of defense for face authentication systems. It is critical to what is critical to liveness detection is challenge response protocols. These are basically where challenges are presented to the user and responses are collected. Common examples are like user tells the user to blink, read, move their head, etc. So for the problems for current challenge response protocols are that they're vulnerable to media-based facial forgery attacks, MFF. The root cause, as determined by this paper, is that there's a lack of strict time verification of a response. That is, the response time is too long and varies among individuals. Adversaries then can synthesize responses faster than legitimate users. So now introducing face flashing, a new challenge response protocol. It significantly raises the bar for launching successful face-off attacks. It works by flashing well-designed photos on the screen and captures the reflected light off the user's face via a camera. It utilizes the following facial characteristics: reflection, unique textual features, and uneven 3D shapes. The fraud detection accuracy is 98.8%, with the worst case scenario being 97.3%, depending on the environment. So the response time is near instantaneous with face flashing, and the simulation time would be much larger for an adversary to falsify this. The security of the protocol is based on time and shape. Or the time module is built using linear regression models, and it ensures that response has not been falsified. Whereas the shape part is uses a neural network model, and it ensures the face shape is stereo and face-like. So the contributions of this paper are, as we previously mentioned, a new liveness detection protocol, face flashing, as well as effective and efficient verifications of timing and face, and implementation of a prototype and evaluations. So diving into the background here, the architecture of face authentication systems can be broken down in the following steps. One, we have a liveness detection module that sends generated parameters to the front-end devices. Front-end displays challenges to users, and then sensors capture the responses. Front-end devices then send the responses to the liveness detection module in the backend, and the liveness detection checks if it's a real human. If so, it sends some of the data to the face recognition module. So some background on the attacks and solutions on current liveness detection protocols is that it can be categorized in the following by the following attacking tree here. So we have both static and dynamic types of attacks, and for each of those, there's both the 2D and 3D flavors. So for a 2D static, an example of this would be a photograph-based attack. This is a dominant form of attack due to its ease of implementation, and it's been pretty much neutralized by existing protocols, example using frequency analysis, etc. And 3D static attacks, an example of that would be like pasting stereo objects on photographs, has been neutralized by existing protocols as well, example computer vision models and others. The 2D dynamic attacks, an example of this would be using advanced models to forge photographs in a dynamic fashion. This paper illustrates that this is the current true threats here to facial authentication systems. And there's 3D dynamic attacks, like example being a flexible screen molded into a face, which would be very hard to launch by an attacker, and it would be too expensive. So here's the protocol process for face flashing. So step 1, we have a random generator of the parameters in the liveness detection module. 2, initialization of the front-end devices. 3, the presentation of a challenge to the user in the form of a flash. And 4, collection of a response using the camera. And the challenge response, step 5, is repeated n times for robustness. So multiple challenge responses. Then we have a time verification, which is ensuring that it hasn't been falsified. And we have a face verification, which shows that, okay, this is a real human. And then we also have the expression verification, like are they smiling, etc. So some of the key techniques to face flashing we'll be discussing are the model of light reflection used, the face extraction process, timing verification, and face verification. So for the model of light reflection used, equation 1, for when the aluminum power distribution E is the same for pixels X and Y, is shown right here in figure in Formula 1, where the pixel is made up of red, green, blue values, where I is the incident light, R is the reflectance, and X and Y are 2 different pixels captured by the camera. This means lights captured by the camera at 2 pixels, X and Y, are proportional to the reflectance of those 2 pixels. And equation 2, illustrated right here, means that for the same pixel point X, even if applying 2 different lights, EC1 and EC2, the reflected light captured by the camera of a pixel is proportional to the incoming light of the same pixel. Alright, so for moving on to the key technique of face extraction, the steps are as follows. Extract face rectangle from each frame using this algorithm 1. Basically just going in, doing an algorithm to track the face based off of those landmarks and form a rectangle. Then use face alignment algorithm to estimate location of 106 facial landmarks. Then, using the landmarks, regularize every rectangle, that is, select the best transformation matrix that minimizes the L2 distance between the regularization target, mean, and the landmark location of the frame being transformed. Alright, so for the timing verification, this is built on the nature of how the camera and screen work. So figure 5 shows the screen and camera effects as the screen is updated from red to green. So in A, we see the screen refreshes row at a time in this direction. And so as it updates each row to green as it traverses down. And the camera refresh direction is column at a time. So the end effect, as this is transitioning the screen, the camera will receive this gradient effect from red to green. So two types of challenges are used. We have a background challenge, which is just a single color flash, and also a lighting challenge with a belt of different color, which is shown in figure 6a. The region of interest, ROI, is the region the camera is scanning when the front end screen is displaying the lighting area. So it's about right here when the lighting area is displayed. ROI is identified as follows. First, calculate the time TU the lighting area begins to be displayed, which is shown in equation 3. So basically we have the beginning time plus the row of U divided by the total number of rows times the second and the time for the frame. And then the next is find the captured frame, which recording period covers TU. We'll call this the kth captured frame. Next, calculate the shift L against the first column of the kth captured frame, equation 4. Basically just calculating where this shift is. 4 linear regression models are then created for inferring the lighting area, as illustrated here in the dotted lines. A weighted average, y hat, is calculated for ROIs across multiple models. In this case, Model 2 and Model 3. There are A columns that ran through the Model 2 linear regression model, and there are B columns ran through the linear regression 3 model, and a weighted vote is performed to produce this y hat. Acceptance criteria is if the mean and standard deviation of the differences between the inferred and actual lighting area are smaller than a predefined threshold. Legitimate responses were determined to be found consistent with the challenges. Also, it produces small mean and standard deviations, as exemplified in figure 7. So we see it in figure A. These are both mirrors, by the way. Showing the corresponding light area. So this is the light in the middle area, and we can see that the mean and standard deviation of this middle area is pretty low. Okay, so for the face verification, after pre-processing, we have a sequence of frames with vibration removed, size unified, and color synchronized. Equation 1 is used to determine the midterm result. Equation 1 was shown earlier. Basically, through equation 1, we can divide all pixels values by a randomly chosen face pixel value. And these are all midterm results of various photos illustrated in figure 8. The observation here is that, as shown in the figure, it is easy to differentiate between real faces and falsities. This is because real faces have uneven geometry and textures. Example of midterm results, A and C are captured from real human faces. B is captured from an iPad screen. D and E are captured from an LCD monitor, and F is captured from a paper. So it's easy to differentiate between these. Based on the observation, the face verification techniques were created as follows. First, abstract. Vertically divide the face into 20 regions, average down to a single vector, and smooth every vector. This will result in images like figure 5C and 9C. It's abstract result. Next, resize the facial region to a 20 by 20 image by bicubic interpolation, resulting in images like 9D. Then, verify by running the resized image through a well-trained neural network. So next, we're moving to the security analysis. We'll start with the challenge response protocol. So face flashing is a challenge response protocol with security built upon 3 elements. One, being unpredictable having unpredictable random challenges. So we use tens of generated images at random, different colors, etc., different areas, etc. So second, hardly forged responses. The light reflecting off a face happens at the speed of light, something adversaries cannot accomplish. And 3, effective response verifications. So we verified the timing of the responses, verified the shape is similar to a real face, and verified that the same face is who we are authorizing. Given the above, it is very hard for adversaries to launch a successful attack. So for this timing verification, some assumptions are that an adversary cannot interpret the screen and then show the latest generated response before the start of the next refreshing period. There always exists some optical sensors collecting light. A delay would occur for an adversary presenting the forged response to a challenge. A delay would cause the 4 linear regression models to do deviated estimation. Part of the region of interest would have already been completed before the adversary is able to forge the response. As shown in this figure here, the figure at the top is our screen, so this is the start of the lighting area when it starts to get displayed, and this is the when it has finished the length of the lighting area. And so as we can see, VK is the time when it actually can start, so there is some delay. Also there would be synchronization issues, etc. So for the security analysis on the face verification, in order to pass the face verification, the 2 conundrums would need to be resolved. Need to conceal the specular reflection of the plane screen, which is very hard to do. And the forged object must have similar geometry shape with human faces while making the requested expression. So here's the analysis against of the protocol against typical attacks. So offline attacks, nearly impossible because the hitting possibility is small, as we require accurate responses to all challenges. If we randomly choose between 8 colors and 10 lighting challenges, the hitting possibility will be less than 10 to the negative 9. Displaying responses legitimately is difficult, as screens produce intensely specular reflection that is easily detectable. MFF attacks, media-based facial forgery attacks, also practically impossible because it would be hard to deceive the timing and face verifications simultaneously. This would require high-quality responses to be created within a couple of milliseconds for attacking a 60 Hz screen. Even if adversary was able to succeed with this, displaying the response is not allowed by the screen. 3D mask attacks. These are impractical because an accurate mask that deceives face recognition module would be very difficult. Also, the mask is hard to be 3D printed and needs human skin reflectance and be so flexible to successfully perform the instructed expressions. So next, we're moving on to the implementation and evaluation. So we'll cover the data collection, timing verification, face verification, and evaluation on robustness. So for the data collection, 174 participants held their phone to the face and made expressions as commanded. Every captured video contained at least 90 frames, and 2,274 raw videos were collected in all under 6 different environment settings. The timing verification, the height of the lighting area was fixed to be the middle of the screen. Then 4 linear regression models were trained using the dataset previously mentioned, and figure 11 shows the performance. So as we can see, this is in order 1, 2, 3, 4 of the models, and we can see that the 2 and 3 have lower deviations, and therefore they perform better, which makes sense because this is the region for the face. For attack simulation, forged areas were fed to the regression models. So here is an example of the forge being shifted from the region of interest, and depending on this shift, with the mean difference in standard deviations is shown here. So as the shift is 0.1, it's fairly small. As it gets large, the median standard deviation gets large, which makes sense. Further, investigation was done under a real-world setting. See Figure 13. So here we have device A is the authenticator, which is a Nexus 6 smartphone in this case, and device B is the attacker, a laptop that reproduces the color displayed on the smartphone video using a camera. This experiment was also repeated by replacing the laptop with a mirror, and Figure 13b shows the delays, with blue being the mirror and red being the laptop delays. So for face verification, we used an open source deep learning framework, CAFE, to train neural network. Using the preliminary parameters of a base learning rate of 0.1, gamma 0.1, momentum 0.9, weight decay 0.0001, and max iteration of 64,000. The negative samples are the adversary videos, which are created from recording the screen that is replaying the raw video, so introducing that delay. And the positive samples are the raw videos. And the results is a 0 false positive rate with 99.2% accuracy. And this is summarized in this table below. Alright, so for the evaluation on robustness, we use the following 6 scenarios for determining robustness in different settings. And this is summarized in the table below. Scenario 1, continuous lighted room, participants as motionless as possible. Scenario 2, participants on a subway train. 3, participants walk on campus. 4, participants hover under penthouses during a cloudy day. And 5, participants walk downstairs. And 6, participants walk down a slope. And the performance is shown in Figure 14. And as we can see, they all achieve very high accuracy. So the conclusion, this paper has presented a novel challenge response protocol, FaceFlashing, which is able to defeat main threats against face authentication system 2D dynamic attacks. Showed that this protocol has strong security guarantees, implemented a prototype that does verification on both time and face. Protocol has high accuracy in various environments and is robust to vibration and illumination. Experimental results prove that the protocol is effective and efficient. And that is all, and thank you for your time.